Thank you. We're here, Courtney and I are here to talk about some practical applications that, yes, I'm short. Some practical applications of global downscaling and climate modeling that we use at Tarrant Regional Water District in operations planning, near-term operations planning, in climate progression, the persistence of climate conditions in our service area, as well as some adaptation that we're using some global climate data for. North Central Texas is the area that our service area is in. We're one of 3 large raw water suppliers in that area. The area has a population of about 7 million today, and projections are to grow to 14 million by 2070. And our service area, outlined in blue, covers about all or a portion of 11 counties. And our population, our portion of that population is 2.3 million now and projected to reach 4.5 million people by 2070. So we have long-term water supply planning is very inherent in what we do, as well as our day-to-day operations. This graphic here shows just a part of our service area that includes our large diameter water transmission system. Our water supply system includes 4 supply reservoirs, 2 in the west and 2 in the east, and is completely dependent upon the availability of surface water. Our large eastern reservoirs supply about 85% of our water needs in our service area through these pipelines, and this system must overcome 400 feet of static head and incurs a huge energy footprint, as you can imagine. We have water treatment plants that are either directly connected to the pipeline or draw from other reservoirs in the service area. We also have several contractual obligations to maintain certain elevations at some of these other reservoirs in addition to those municipal water supply needs. So we use those other reservoirs as terminal storage. So forecasting the supply needed to meet these demands every year is a challenge. Even though our service area population is growing, municipal demand projections are relatively stable and have a variability factor of about 2 from wet to dry conditions and in seasonal variability. But our real challenge is the variability in our terminal storage needs within any given year or from year to year. And they can vary by a factor of 7 or even 12 in some cases. So as temperatures and water demands increase as our summer approaches, our supply flows in our pipeline are more and more allocated towards municipal water treatment plant demands. And at the same time, the water levels in our terminal storages are decreasing. So to avoid overtaxing our system, in the heat of a summer, we move large quantities of water all year round to these terminal storage reservoirs. And it's based around predicting natural runoff. Those demands can vary based on the incredible range of hydrologic inflows possible. Additionally, we must plan for long periods of up to a year or more to ensure that we're optimizing our surface water supplies with respect to seasonal variability. For example, we don't want to incur large costs to struggle to meet an elevation goal at a terminal storage reservoir if Mother Nature is going to assist us within a few months. So to model for day-to-day supply operations planning, as well as water supply reliability, we use Riverware. You may be familiar with it. The University of Colorado at Boulder has developed this modeling system, and it is in wide use at TVA, the Bureau of Rec, and the Army Corps of Engineers, as well as many reservoir operators in Texas. This model can be infinitely customized to represent a riverine system with solution methods at various points and a rule set of our operating policies and priorities applied. The input for our model is mainly the hydrologic inflows to these reservoirs that express that wide variability of possible climate conditions. We have observed hydrologic inflow records, which are key. Our 86-year period of record of hydrologic inflows and evaporation data, some observed, some synthetic, that we can use. And this period spans those extreme wet and dry conditions that we have experienced in our service area. As Mr. Slusher mentioned earlier, the drought of the 50s is our currently considered our drought of record, and is what we plan all of our extreme conditions around. Our water supply, our operating rules, et cetera, are all based around that period of the 1950s. So when we first built this model, we used, the model operator would guess as to what the current climate state was and what it would likely be for the near future to initialize that forecast state. And then a Markov chain process is used to resample those historic observed hydrologies based on the likelihood of a wet or dry condition persisting or transitioning from one state to another. It prepares 100 separate hydrologic input files that we use for a stochastic run in this model. More recently, we worked with Hydros, a consultant in Boulder, to develop a downscaling tool that is specifically developed for TRWD in our service area. We're all familiar with short and long cycle weather patterns such as the ENSO and the NAO and others. These are also known as teleconnection patterns. The term teleconnection pattern refers to a recurring and persistent large-scale pattern of pressure and circulation anomalies that span vast geographical areas. Our consultant has experience in developing correlation between microscale, geographically specific weather and inflow data to this large-scale global data. They were able to use a publicly available weather data set and develop a system that scans these data sets and our inflow records and correlated them to a large range of these global atmospheric predictor variables. So Courtney is going to tell you some more about the meteorological variability in Texas, as well as some of the complex predictor data that was used in developing this tool.
Thank you, Laura. So North Texas climate specifically can vary tremendously throughout the year, just like many regions we know in Texas. So this graph here, this shows the monthly climate normals at DFW for both precipitation in green and the temperature normals there in red, brown, and blue lines. So May and October, which I saw in Austin as well, this is kind of the same thing. It's generally the wettest months of the year, and it accounts for more than 25% of the average annual rainfall, which is 36 inches at DFW. And then the late summer months are usually the driest. Now the driest months are also the warmest, and daytime temperatures frequently exceed that 100 degrees Fahrenheit. So these dry and warm summers, which I think is mentioned a few times, it can really exacerbate the soil moisture conditions and then dry them out very quickly. Now, TRWD spreads from Wise County, as Laura showed on the map, to Freestone County, and we have a very wide climate variability just within that sector. So Bridgeport, on the far northwestern zone, they can see an average around 35 inches per year, while Ross, they're near Cedar Creek Reservoir, they see an average of about 40 inches per year. Now, those are the averages, but we've been talking about extremes this whole morning, and that's very common in Texas. So precipitation can vary at DFW. They've seen 20 inches in 1 year to more than 60 inches of rainfall per year. And for us, the wettest year recorded was in 2015, where we saw over 62 inches of rainfall. In many areas just in North Texas, we saw a complete year's worth of rainfall in May of that year. Now, 2015 also happened to be the wettest year statewide, and many of you probably saw the graphic on the right-hand side at 41.23 inches, and that's when the National Weather Service posted this graphic here. And it stated that 35 trillion gallons of rain fell, which was enough to cover the entire state of Texas with 8 inches of rain, or supply the entire world's population with 10,000 days of water. Very impressive. Now, in Texas, drought to flood and back to drought again can occur rapidly or with a dice. We have lots of 1s and 6s from this morning. So this graph here, this shows the percent of the state in drought since the year 2000. And in 2011, after many months with little rainfall, and the record here in Austin with huge amounts of maroon there in the middle, there was more than 85% of the state in D4, and I think we saw that graphic this morning, followed by many more years of little rainfall until 2015 when it was completely eradicated and wiped away on the state. And then drought briefly returned in 2018 until October, when an abundance of rain fell and remained through the early summer of 2019. Now we have drought returning, and we're looking to see what is in store for us in 2020. So to help TRWD with these extremes, the forecasting tools really needed to grow in complexity. And the latest set of tools are derived from the Modern Era Retrospective Analysis for Research in Applications version 2, or just for short, MERA 2. This data set is a long-term record of global atmospheric analysis, and this starts around 1980. And this assimilated data can include ground or airplane-based measurements, satellite-based infrared, microwave, GPS occultation measurements, and really over time, the technological improvements that we've seen. This has increased those data points exponentially, as seen there on the graphic. So with the inclusion of the IASI A and B, now the current monthly data is up to 70 million data points around the globe that we can use. So using the MERA 2 data, these are the atmospheric variables that statistically correlated with inflow into TRWD's reservoirs. Correlations to TRW inflow were calculated at all pressure levels, all the way from the surface, all the way into the upper atmosphere every month. And atmospheric variables include temperature, zonal meridional wind speed, relative humidity, and many others seen on this list here. So one of the things we found interesting was predictors could vary from 15 in the month of September all the way up to 246 in the month of May. Now, to see where all of these predictors are located, here's the Google Earth representation. And the colored blocks represent either an individual parameter or a relationship between two parameters, and generally between 40 and 50 kilometers wide. Clusters vary in size from 1 block up to 577 blocks. You can see there over Russia, just west of Lake Baikal. For temperature, and really, go back to that one. And at that point, you can really start to grasp the extent of variables. I think it might be a little behind now. But really, these, being a meteorologist, I wanted to know why. So why do temperatures around the Great Lakes region over to Maine correlate to North Texas? Why does the covariance of relative humidity and meridional wind over Mexico correlate? Why do temperatures in Siberia matter to us when you're looking on this globe? So I want to look at just a few examples. So here's the first example. So here's 312 temperature boxes at the month of March clustered over the Great Lakes region there. And these are at 32,000 meters in altitude. And then these are related to the Arctic Oscillation. And this determines the degree to which Arctic air can penetrate down into the middle latitudes. So think of the Arctic Oscillation really as the flippers in a pinball machine. And when they flip negative, that polar air, also known as the polar vortex, that is the ball, and it gets pushed down into the middle latitudes. And what that means for us is that that frigid air reaches Texas, allows more frontal boundaries to come through all the way down, and higher rain chances really along with them. So here's a second example. This is a cluster of boxes with the covariance of zonal wind, and that means west to east wind, and humidity in May on the eastern coast of Greenland, and those were correlated to us. Now, once again, this is most likely due to the negative phase of the Arctic Oscillation. It causes that jet stream to buckle. During the negative phase, Greenland typically sees a warmer than normal season, an increase in humidity, and weaker zonal winds. And remember, both correlation and anti-correlation matter for those two variables to be significant for North Texas. So the Northern Atlantic had the most concentrated areas of predictors than any other area around the globe, and this really surprised me when we were looking through this data. So there were around 300 boxes of zonal wind, that's that east to west in yellow there. There were 400 boxes of geopotential height in black there. and almost 600 temperature blocks in white at the various altitudes. And these were related to the North Atlantic Oscillation, the NAO, and that's a climatic phenomenon that controls really the strength and direction of westerly winds and storms that go across the northern Atlantic. And that's measured by the difference in pressure at sea level between the Icelandic low and the Azores high. So during the positive phase, that area of low pressure you see there, that really intensifies, and consequently, it strengthens the power and direction of those winds going across the Atlantic. Now, what we found was that the geopotential height and temperature there, they lie directly below the location of that intensified low, and the zonal wind, there in the yellow, that lies directly in the path of that intensified jet stream, which correlated back to us. Now, interestingly enough, here's what we found. In 2015, the positive phase remained from January through June, when North Texas got almost a full year's worth of rain. So really good correlation to those factors. Now, we hear a lot about the El Nino Southern Oscillation. It's based on the sea surface temperature departures from average in the Central Pacific, but the other half of that equation is the air pressure difference between Darwin, Australia, and Tahiti, and that's tracked by the Southern Oscillation Index. So the SOI is negative during El Nino when the air pressure is abnormally high over the western tropical Pacific and abnormally low over the eastern tropical Pacific, and then the opposite is true for La Nina. So during El Nino, trade winds are a lot weaker in the lower levels, and this in combination with those warm waters allows for an increased presence of storms across the Central Pacific. And these storms can really alter the air circulation in the upper atmosphere and lower the air pressure at the surface. So during La Nina, cold upwelling increases along the coast of Chile, and trade winds are stronger in the lower levels, pushing all those warm waters to the west, and that's where storm development is more likely. So what did we find? Well, all the months that correlated matched up with the months that El Nino, La Nina have the biggest known impacts in North Texas, which is generally the late fall and the early winter. Now, during an El Nino, North Texas, we generally see that above average precip, but what really surprised me about these clusters of variables was that they were really small. There were a lot less than we saw with some of the other teleconnections near Darwin and Tahiti. So that was surprising to us. Now, some of the covariance variables had higher signals in this region, those purple and green, which represent how one data set can closely relate to another. We would expect, as those trade winds decrease during El Nino, the humidity would increase at locations near Tahiti and then vice versa for La Nina. Based on this, a strong negative covariance would relate to the impacts of weather in North Texas during those winter months. So here's Laura to tell you how we have used all of these predictors globally.
So, the way that we implement this data, we had, as I'd mentioned before, we had used to initialize our operational model and the 100 stochastic runs. We would use an initial, just a guess at what, ask Courtney or look outside what the weather is like and what it could be over the next couple of months. But this tool now gives us an opportunity to look deeper into what the likelihood of the existing condition is and what that condition is likely to persist or transition to within the next couple of months, so that we can more intelligently inform and initialize our operations model. So this project had a goal of determining if the skill of the predictor variables was at least twice as accurate as that initial model guess or conventional meteorology for this tool to be considered a viable alternative. Analysis of the results demonstrated that these predictor variables are indeed accurate 75% of the time in predicting an actual local climate condition, and 95% of the time accurate in predicting at least a neighboring state. So it's important to remember that the predictors that we're using are used to correlate to historic hydrologic inflows. We're not predicting a weather model. We're performing a statistical correlation of those predictor variables to observed hydrologic inflows. We use that correlation to predict what the hydrologic state will be of our reservoirs and what those inflows will likely be over that planning period. So another power of our hydrologic records is the likelihood of transitioning from one state to another. Some transitions are more certain than others, such as starting in a dry state in July and persisting in that same dry state into August. The probability of transitioning from a wet state in April to a wet state in May is also highly likely. Other states are not so likely, such as transitioning from a dry state in June to a wet state in July. So using this global downscaling method to determine the initial climate condition with which to initialize our model, and then the transitional probabilities for the likely climate progression after that can take over. And using those tools, we then regenerated our set of 100 hydrologic inflow forecasts for use in the stochastic run. Those are produced to match the probability distribution of that global downscaling tool. The historic inflow data set is sorted into bins, and then the Markov chain process resamples that observed historic record to generate those number of traces to match the probability of a bin. For example, if the dry category bin is 37% probable, then 37 of those 100 traces are generated with the dry initial condition and a dry transitional progression. And this entire process is run every month using that distinct set of predictor variables that demonstrate skill for each of those months. So, I remember Mr. Smith talking about the difference between projecting and predicting. And unfortunately, we don't have that luxury. We must project a plausible range of conditions and as well as predict the most likely of what those conditions are to be to devise all of our operational plans, optimize our surface reservoir storage and supplies. And this graph is just one of the parameters of the output of that 100 runs, where all of our operating rules are then overlaid on top of the hydrologic progression. So we get a cloud of probability of lake elevation forecast. This is one of our lakes, one of our supply lakes, and then given that initial condition, there's the likelihood of where we're going to be. So you can see it's kind of all over the place. We use these outputs to try and inform how we're going to devise our pumping plans to calculate the likelihood of reaching a trigger where we need to be engaging our pipeline to move water into one of these reservoirs and recharge it. So since that is a little bit of a mess, we do break it down to a statistical sampling of those 100 runs. And this is just an example. That's that same forecast that was run beginning in June of 2018. The black line is the actual elevation overlaid over what the percentile representations of that cloud of probability was. It's a little bit easier to read than the full 100 results. We can communicate the probability of reaching a target elevation where pumping may be required. It's also important to remember the scale of the kind of predictions that we are focused on. We're trying to accomplish the task of predicting when hydrologic inflows would occur. That will help design our pumping plans and guide us in engaging that very expensive pipeline. So we're not highly focused on inches of elevation within a time span of days. We use this pipeline to supplement storage in these reservoirs at great expense and over very long periods of time. If we can better predict the likelihood of natural recharge over these long periods, then we can avoid transporting large volumes of water that could ultimately be discharged over a spillway. So periodic rains can fall that can change these plans. And we are actively engaged in rerunning this process on a monthly time step. We want to make sure that we reinitialize the model, reinitialize the stochastic generation of the hydrologic traces, and rerun this process every single month. So it's a guideline. It doesn't give us a deterministic path forward, but it does give us a probabilistic approach. So we've also used this riverware model to perform other studies of climate extremes. We've heard multiple times today, there is a need to simulate extreme conditions of longer duration given the onset of persistent climatic changes. Our human records are worryingly short. Our period of record only extends for 85 years. And as many have posed the question, what if prolonged severe drought conditions that are longer than our historic drought of record are possible? What if more intense cycles are now a permanent part of our climate? We could generate a worst case scenario of 100 years with no hydrologic inflow, but is that really informative in future water resources development? Would I build so much reservoir storage that I would never run out of water during a 100-year drought? And as you all know, that would be prohibitively expensive. So our intention with this climate progression kind of exploration was not to demonstrate disaster, but long-term climate trends, the cycles of drought and recovery that naturally occur within our service area, within the North Central Texas area. And we needed to extend our historic period of record. So as a couple people have mentioned already today, we went searching, found a likely suspect, the paleoclimatology. The NOAA Paleoclimatology branch performed studies to translate tree ring samples into annual average Palmer Drought Severity Index values, which are a measure of soil moisture and drought. So these tree ring studies have been used to correlate and recreate climatic history. The reconstructed PDSI record for the TRWD service area extends from 996 AD to 2003 AD, 1,008 years of reconstructed hydrologic history. So the first thing we did, you've seen this graph similar to this in the handout that's in our booklets. The red is our instrumental observed PDSI values, and then the blue is the reconstructed PDSI from the tree ring studies. So what we did was we took a similar value approach and mapped the closest matching yearly value in the observed record to the reconstructed record and tracking which year we were matching. And this is what it looked like when we finished matching values back over from our known observed record back over that paleo record. So there were extremes in the reconstructed period that we did not have in our period of record. So to limit the synthetic hydrology that we were constructing, we limited those extremes to the known instrumental PDSI values because we just didn't have hydrology to match those extreme dries and extreme dry and wet periods. So it could be more, the results of this modeling could be a lot more extreme, but we did limit it to what our observed records were. So the next step, we took the hydrology for each known year in the monthly time steps. We know that we're making some general assumptions here about the average annual PDSI value in the hydrology for an entire year, but we decided that this was a sufficient approach to demonstrate climate progression over a multi-year or multi-decadal period. And this demonstrates how the hydrologic paleo record might have looked given the climate patterns suggested by the tree ring data specific to our service area with the probability of the dry or wet persistence. Let's see if I can make this laser work so that, probably not. Oh, ta-da! So this here in this red area here, which is our observed historic record, this circle represents the drought of the 50s. And this is for one specific lake. This is Bridgeport Lake. And as you can see, it doesn't look like that's all of that extreme. When we map out those known and match them to the known hydrologies and match them to the extended period of record, we come up with much longer, more protracted dry periods, more severe and of longer duration. Here is that period in the 1100s. That's the one that a lot of people focus on. There's archaeological evidence of a megadeath in the North American continent, Mesoamerican flora and fauna, an extreme die-off in that period. And then here, there's a period of extreme dry centered right around the Civil War. So the takeaway from this is that our drought of record, the one that we devise all of our water resources around and our reliability and our operations and all, simulate all of our reservoir storage conditions, is not that extreme. And so we wanted to take this as an opportunity to take this synthetic record and put it through our riverware model and see how our operational rules and our reliability held up to some of these more protracted records, more severe and dry periods. So this is, and I realize this is a little busy, sorry, but this is the resulting elevation of that same reservoir, Bridgeport Reservoir, for the 1,008-year period of record using that reconstructed hydrology. The good news is that our system is pretty robust. We can use this model to overlay forecasted future demands and see how our operational rules are performing in terms of reliability. It got pretty scary at some times. You can see where the reservoir did get a little bit low, but none of them ever ran dry. So it was encouraging that our system is, at least theoretically, more reliable through some of these more extreme periods. Another way that we're using global climate data is a climate adaptation, where a specific application that we're currently and just in the beginning of, so I don't have a whole lot of information on it, but we're just devising a study on looking at perturbing projected demands in the future. So the way that we currently model our demands is we'll take a future year projected demand scenario and then perturb it a little bit based around, the climate condition that is expressed from the hydrologic record. And we wanted to see if we could perturb that demand projection a little bit more. And so what we did was, and all the credit goes to CDM Smith because they're the ones that are doing all of this work, but they took groups of climate models and grouped them in this grid pattern. And as Mr. Smith mentioned earlier, instead of using just one model, we're using groups of models to kind of bound the possible future scenarios of what that demand variability can be. So we've currently come up with two scenarios, the hot, dry, and the warm, wet, and using kind of the average of those grouped climate models to then produce what our forecasted demands will be. Forecasted demands in 2070 for 4 million people can be, as much as 25% higher than what we're currently modeling in our current system. So it's important to us to make sure that we're prepared for not only the hydrologic condition, but also the demand. The demands on our system that will be required to supply. So just to kind of recap where TRWD is using global climate models in our operations and planning. We've got our short-term ops forecasting where we're and guessing, making a informed guess at to what our near future state is going to be. We've got our long-term planning studies where we're looking at climate progression, the likelihood of persisting from or changing from one state to another, and then climate change in looking at how our demands may be impacted by climate change in the future. Thank you.